Alright, in this one a bar magnet's moved through this circular loop here. It moves through the constant speed, and an EMF is generated when that happens. So an EMF is a voltage. It's generated in the while loop when that happens. The while loop's connected to an oscilloscope, which is this thing here, and that just measures the voltage. It measures the voltage. It might look like that, I'm not sure. We're going to actually answer that question soon, what it looks like. But for now, just let you know what the oscilloscope is. The first question I was asking, why is an EMF generated in the while loop? So I'm going to work backwards for this question, and I'm going to say, why is an EMF generated ever? Due to Faraday's law, an EMF is generated when there's a change in flux. In a wire loop. So that's my first one. My second dot point, because this is 2 marks, I'm going to explain where does the change in flux come from. So I've just explained Faraday's law. So there's an EMF generated because there was a change in flux in the loop, but why is there a change in flux? Now, let me explain first. There is a change in flux because as this magnet comes in from this side, so here it is coming in, and it gets closer and closer and closer. It's got field lines which come out of the north and into the south. Right, if we extend these field lines out like this, you see only one of these 3 that I've got at the moment goes through that loop, and as it gets closer and closer to the loop, more and more field lines go through that loop. So as it gets closer and closer to the loop, the flux through the loop increases, and that's why there's a change in flux. So that's what I'm going to explain now. As the magnet gets closer to the loop, the flux through the loop increases, and this is the change in flux. So just once more, we'll explain why is EMF generated in any occasion, because there's a change in flux, and what's the change in flux in this equation. Alright, let me open up the file for the next one. Alright, question 11. On the graph on the axis below, sketch the variation of EMF with time from when the magnet's a long way to the left through the loop to when it's a long way to the right. Note you can either take upwards or downwards as positive. Alright, to get the EMF or the voltage, we first want to know what's happening to the flux. What's happening to the flux through time. This is just a little graph that's going to help me. And then to help me do that, I'm going to draw down here I'm going to draw my loop. I'm going to draw my magnet as it's far away, as it's getting pretty much inside the loop, as it gets far away again. Now, I'm not going to draw all the field lines, but as it's far away, the flux through the loop is very small. So as it's very, very far away, the flux slowly increases, and it gets faster and faster, and more increase. As it goes through the middle, the flux is at its maximum, it doesn't change. For the length of this whole magnet from here to when the magnet's through the loop, the flux is at its maximum. So it levels off and nice and flat, and then as it goes out the other side, the flux decreases again as it gets further and further away. It's meant to be nice flat. like that. So now how do you get from flux to EMF? That's through Faraday's law. EMF equals N, change in flux over change in time. Now this thing here means gradient, because this is flux time graph, change in flux over change in time, gradient. So if I can take the gradient of this graph, I can get the voltage. So let's have a look at the gradient. Right, well the gradient, the easiest part to talk about the gradient is in the middle here. When it's really flat, the gradient's 0. So even though this is high on this one, a high value, its gradient is 0 because it's flat, completely flat. So in the middle here it has a value of 0. At the start here it starts off flat and the gradient increases. Not only does the value increase here, but the gradient gets steeper and steeper and then smaller and smaller. So my values here have to start off at 0, get bigger and bigger, and smaller and smaller. Okay, this is the steepest part here, which corresponds to the highest value here. Levels off, comes down. 0 gradient, 0 value. Here, we're going to increase the gradient, increase in gradient, so an increase in value, but it's in the negative direction. Increase in gradient, and then it's going to be back to 0. This must be like that, because we get it at its steepest negative value, and then it slowly gets, the gradient gets smaller and smaller along here, back to 0. Steepest negative value, or largest negative value, back towards 0. And that's that one. Number 12 is probably the hardest question that students find in this exam, which is Lenz's law. Now this one here, after the magnet's passed through the while loop and is moving away from the while loop, so pass through and then moving away, current flows around the loop anti-clockwise. So they've given us the answer in this one, and they want us to use Lenz's law to explain why that's the answer. So they've given us the answer, we have to do the explanation. What I've done is I've copied and pasted the picture here to make it easy for ourselves. So they've asked from through the while loop, that's position 1, to moving away from the loop, position 2. And we're as viewed from the left. So we're viewing this whole situation from here. So we're here looking that way and looking at the situation, and they are saying from here the magnet moves to here, and it makes an anti-clockwise current. So what I'm going to do is I'm going to draw the loop again. I'm going to draw it up here, looking from this guy. So looking from this guy, he sees this loop, and this is position 2. Let's label this so that people can see. This is our magnet pass through, to magnet moving away. Okay. What is the field doing in this situation? Well, here's the magnet, and that's position 1, just so we can label it, just so you know what I'm talking about. That's position 2, and these diagrams at the top here are position 1 and position 2. If I was looking from the left, which is what they want us to look from, viewed from the left, that's position 1, position 2. The field here comes out of the north into the south. Here's the same, out of the north into the south. Okay, lots of field lines going through the loop here. These ones here are going to miss the loop, so hardly any field lines when it's in position 2. Looking from number 1, these arrows are going towards him. These arrows are going towards the guy who's looking. And what does he see? He sees those arrows coming towards him, so he sees them coming out of the page, and they are dots, not crosses, they're dots. So he sees a lot of magnetic field in position 1, that's here, lots of field lines, and hardly any field lines in position 2. Now we can see the flux has changed. Because the flux has changed, that's why there was a voltage measured, which we had before. And now we've got to say, which way is the current going? Is it going around this way or around the other way? Well, the answer says already that it's in an anti-clockwise direction. We have to now show that. So the way we're going to do it is we always write down Lenz's law, which we've got on our cheat sheet somewhere. Lenz's law says a current gives rise to a field, magnetic field, to oppose the original change in flux. And the other way that I've been telling my class how to do it is we write down here somewhere, this is all stuff we can cross out, this is our main answer over here, but this is to help us figure it out, is I like things the way they were. I like things the way they were. So how were things in this case? Things were, well, the field lines, there was lots of them coming out of the page, and now there's hardly any of them coming out of the page. So because the coil liked having the field lines coming out of the page, it's going to make field lines coming out of the page. So in position 2 will therefore make field lines out of the page. And if we use our right hand solenoid rule, if I was to grab that with my fingers around there, my thumb comes out, I get anti-clockwise. So then my last dot point is this field is induced, is made by an anti-clockwise current. And I can cross out my working here because they don't need to see that. And I'm just left with my answer. I'll cross that out as well. Left with my answer there, I'll cross that out.